Good morning, dear students, and once again, welcome back to our course. In the last lecture, we discussed in detail about the concept of Thevenin's theorem and Norton's theorem. And I told you that what is the meaning of Thevenin's theorem and what is the meaning of Norton's theorem and what are the applications of these theorem. For example, if you have a network, a linear bilateral network, and suppose if you want to convert this particular network into an equivalent voltage source in series with its internal resistance. That means if you want to represent this entire complicated network like a kind of voltage source in series with its internal resistance across a load terminal, then in that case we need to apply the concept of Thevenin's theorem to find out the value of this VTH, which is called as Thevenin's equivalent voltage, followed by this RTH, which is called as Thevenin's equivalent resistance. In the same way, if you want to convert and represent this network into an equivalent current source or practical current source, that means a combination of current source in parallel with its equivalent resistance, then in that case the theorem which we need to apply is called as Norton's theorem. Or simply, if you got the Thevenin's equivalent of a given network, then we can apply source transformation method or source transformation technique to represent this Thevenin's equivalent network into its corresponding Norton's equivalent network. So it is something like this. So it is going to be a current source. In parallel with that, we need to indicate its internal resistance, and here we need to connect a load which is nothing but say RL. Now this is going to be IN and this is going to be RN, where IN is Thevenin's equivalent current source of the given network, which we can write like VTH divided by RTH, and this Rn is going to be equal to what? RTH, because ultimately we have applied here source transformation method or source transformation technique, and I told you that while applying source transformation method or source transformation technique, the internal resistance of the source will remain same. So here previously we have RTH, so same RTH supposed to be connected over here. So this portion we have discussed in the last class, and then we also solved some numerical on how to find the Thevenin's equivalent of a network which is given to us, which we are asked in the previous gate uh, exams. Now let us continue by solving some numerical on Thevenin's equivalent circuit, and then in this particular session we are going to discuss the last theorem as far as gate syllabus is concerned, and that is nothing but the application of maximum power transfer theorem. What is maximum power transfer theorem and how maximum power transfer theorem plays an important role in order to analyze the behavior of a circuit, that we are going to learn in this particular class. So let us start with our session. So first we are going to solve a numerical on Thevenin's theorem, and our objective is to find the Thevenin's equivalent for a circuit that is given to us, and the circuit is something like this. Here we have a current source of value 5 ampere, and then here we have a resistor of value 4 ohm. Then somewhere over here we have a 2 ohm resistor, and then here we have a voltage dependent voltage source. Now this is very important. This is, I think, a very first kind of numerical which I'm going to take on Thevenin's equivalent circuit calculations, where we have dependent source in the circuit, and our objective is to find out its corresponding Thevenin's equivalent circuit. So here we have a voltage dependent voltage source and the value is 2 Vx. Now what is Vx? So Vx is going to be a voltage across this 4 ohm resistor with this polarity plus minus. So this is given to us, and then the circuit continue like this. So here we have again 6 ohm resistor, and then here we have one more resistor of value 2 ohm, and across these two terminal, that means terminal number A and terminal number B, when you see this circuit through this particular terminal, whatever the Thevenin's equivalent voltage and Thevenin's equivalent resistance which we are going to observe, that we need to find out. So our objective is to find the value of this VTH and RTH for this particular circuit. Now, as far as this circuit is concerned, here we have a combination of dependent as well as independent sources. So this 5 ampere is independent and this 2Vx is a dependent kind of source. Now in this case, how to find the value of VTH and how to find the value of RTH, that is very important. VTH is quite simple, but for calculating RTH, it is very difficult. So how to solve this, that we are going to look. So first, let us try to find out its Thevenin's equivalent voltage. And I told you in the last lecture that in order to find the value of this VTH, what we need to do, first of all, we need to identify the load terminal where we need to calculate the value of VTH. So here by default it is given in the numerical that we need to find the value of VTH across terminal A and B. So these are nothing but our load terminal, and we have to find the value of voltage which is supposed to be developed across these two terminal. So how to find this? So in order to find the value of this VTH, first of all we need to assume some value of current which supposed to be flowing this particular circuit because of this and this kind of sources connected in the circuit. So what we need to do, let us try to assume some value of current in the circuit. Now see here, we need to find the value of this VTH, and VTH is nothing but the voltage across terminal A and terminal B. Now because this part is open, so whatever the voltage which we are going to experience across this 6 ohm resistor, the same voltage is going to be appear across terminal A and B. So VTH is simply the voltage which we are going to experience across 6 ohm resistor. This is very important. Now let us try to assume that the value of current flowing through this particular mesh is, say, I. I've just assumed that the current will flow in the clockwise direction in this particular sense. It may possible that you may assume the current in the anti-clockwise direction, and I told you that if you got the same value of current, that too in positive sense, whatever the assumptions you have made are nothing but correct. And suppose if you got the value of current in the negative domain, that means the actual value of current which is flowing in the circuit is opposite to the direction of current which we assumed to solve that particular numerical. This is what the basic philosophy that we need to implement. Now let us try to apply Kirchhoff's voltage law in this closed loop, this one. That means let us consider that this terminal is say C, this terminal is say D, this terminal is say E, and this terminal is say F. So C, D, E, F, I'm going to apply Kirchhoff's voltage law. Now when we are moving through this 4 ohm resistor, we will experience a voltage rise of magnitude Vx. So I am writing here as plus Vx. Then when we are moving through this element, again we are going to experience a voltage rise because we are moving from negative to positive. So it is going to be plus 2Vx. And then when we are moving through this 6 ohm resistor, because we are moving in the direction of current, so current is from upward to downward, so this is going to be plus to minus, and that's why we need to experience a voltage drop, and it is going to be like minus 6 into I. This is going to be equal to what? 0. Now let us try to find out the relationship between Vx and I. So I am writing here 3Vx is going to be what? 6I, or simply Vx is going to be 2 times of I. This is important, or this will be your equation number 1. So Vx is going to be equals to 2 times of I. Now let us try to find out one more relationship between Vx and I. So how to find out that? Now just focus on this element which is nothing but a 4 ohm resistor. Now through this 4 ohm resistor we have a combination of two circuit currents which are flowing simultaneously. First one is your 5 ampere which is supposed to be flowing in the downward direction, and second one is I, which is nothing but the loop current available in this particular mesh. So suppose if I am interested to write down the equation of Vx in terms of 5 and I, so what it will be, it is something like that. See here, let me draw that element over here. This is nothing but a 4 ohm resistor. On one side we have a current of 5 ampere, and on the other side we have a current of magnitude I. And because the polarity is known to us, see the polarity across this 4 ohm resistor is plus minus, and the value is say Vx. So here we have Vx and that to polarity plus minus. Now because it is a passive element, and in case of passive element I told you that the resultant current must enter through positive terminal, and in this case because 5 ampere is going to enter through positive terminal, that's why we need to assume that if you want to calculate this Vx in the positive sense, this is going to be equals to V is nothing but I into R. So first we need to take R, which is nothing but 4 ohm, multiplied by I, which is nothing but the resultant of this 5 ampere and this unknown I. So it is going to be 5 minus I. This is very important. Now why I have written 5 minus I? Because if you see 5 minus I, the resultant current has to be flow in downward direction. And why I have considered this as a downward direction? Because the polarity is plus, and because it is a passive element, I told you that current always enter through positive terminal in case of positive element. That's why Vx is going to be positive when 5 minus I into 4 we are supposed to take. So this is the second relationship between Vx and I. So if you further solve this, I can write here as Vx is going to be equal to 20 minus 4I. This is very important. Now our objective is to find the value of this I, what this I is going to be. And to calculate that, we know that from equation number 1, Vx is 2 times of I. So I can write this Vx as 2 times of I, which is going to be equal to 20 minus 4I. So if you solve for I can write here as 6I going to be equals to 20, or I can write here as I is going to be 20 by 6, or it is simply 10 by 3 ampere. Now see here, the value of current is positive. That means the direction which we have assumed initially in this mesh, which is in clockwise direction, is correct. Suppose if we got the value of current as negative, that is minus 10 by 3 ampere, then in that case the actual value of current flows in this particular mesh will be in anti-clockwise direction, which is nothing but ulta, exactly ulta. So this is very important. So we got the value of current I as 10 by 3 ampere. Now we are going to calculate the value of this VTH. So how to calculate VTH? So this VTH, suppose if you assume that this is going to be plus and this is going to be minus, so here we have VTH. Because it is an open path, so the current flowing through this 2 ohm resistor is going to be 0. So VTH is simply the current which we are going to experience across this 6 ohm resistor, and it is nothing but V into I. I into R, where I is nothing but this I, which is nothing but 10 by 3 into R is nothing but 6. So I can simply write here like this: VTH is going to be equal to what? I into R. Now what is I? Just we have calculated I is nothing but 10 by 3 into R, which is nothing but 6 ohm. So this is going to be like 3 ones are 3 twos are 10 into 2, that is 20. So VTH, that means the Thevenin's equivalent voltage for this particular circuit we got as 20 volt. This is very important. So the first part of this numerical is over. Our objective is to find the value of Thevenin's equivalent circuit of this network, and for that we need to find the value of VTH followed by RTH, and finally we got the value of VTH as 20 volt for this particular case. Now let us try to find out the value of RTH. how to find the value of RTH. Now see here, in order to calculate the value of RTH, we need to apply deactivation rule. That means to find the value of effective Thevenin's equivalent resistance across load terminal, whatever the sources, when I say sources, they are strictly independent sources. All the independent sources available in the network we need to deactivate. And when we have independent voltage source, we are going to deactivate them by short circuit. When we have independent current source, we are going to deactivate them by open circuit. So these points we have already discussed. Why to deactivate voltage source we need to short them, why to deactivate current source we need to uh, open circuit them. These points we have discussed in the previous section. So apply that logic and let us try to redraw this structure. So to calculate, I'm writing here calculations for RTH, we need to apply deactivation rule, and whatever the independent active elements available in the circuit, we need to deactivate them all. So here we have only one independent active element, and that is nothing but 5 ampere current source. Now because it is a 5 ampere current source, to deactivate them we need to replace them by a open circuit condition. So the circuit is something like this. So it is going to be like a 4 ohm resistor, then somewhere over here we are having 2 ohm resistor, and then here we are having a dependent voltage source, and then here we are having a 6 ohm resistor. This is going to be 4, this is going to be 6, this is going to be 2, and here with the polarity say minus plus, here we are having 2Vx, and this is going to be plus, this is going to be minus Vx, and then here one more resistor of value 2 ohm, and then we are having a circuit like this. This is going to be terminal A and this is going to be terminal B. Now see here, our objective is to find the value of RTH across terminal AB. Now to find the value of RTH, we must know what will be the resistance offered by this dependent voltage source, but we don't know its internal resistance. So how to find this value of RTH? Now this is important portion of this particular numerical, because we know that how to find the value of RTH. If you have only independent kind of sources, it is very simple to find the value of RTH. The thing is that we need to apply deactivation rule. When we are dealing with voltage source, simply we need to short circuit them. When we are dealing with current source, simply we need to open circuit them. But if we have a combination of dependent as well as independent active elements available in the network, then in that case it is very difficult to find the value of RTH, because once we apply deactivation rule, that is applicable for only independent sources. But if we have a dependent kind of active element, then how to replace them by its equivalent internal resistance? It is very difficult because we don't know what will be the internal resistance of this 2Vx. Then in that case, to find the value of this RTH, we need to apply the concept of Ohm's law. And according to Ohm's law, we can write here as V is going to be equals to what? I into R. Now to calculate the value of R, I can write this equation as R equals to V by I. So this technique we need to find or implement in this particular case. So here our objective is to find the value of RTH. So what we are going to do, we are going to connect a very small value of voltage source in this particular circuit, which is nothing but across terminal A and terminal B. That value may be anything, but normally we take that value as 1 volt. So we are going to connect 1 volt active element in this particular circuit, and we are trying to find out that how what will be the value of current supplied by that 1 volt voltage source. So first we are going to calculate the value of this I. Once we know the value of this I, we know the value of this V, which is nothing but 1 volt. So simply we are going to apply Ohm's law, which is nothing but R equals to V by I to calculate the value of this R. Now this R is nothing but the resistance across terminal A and terminal V, which is nothing but what? RTH. So this R is going to be equals to what? RTH. So this is what the basic philosophy which we need to implement over here to calculate the value of RTH. And this is only when we are dealing with dependent type of active elements in case of Thevenin's equivalent circuit or Norton's equivalent circuit. I hope this point is clear to everyone, because it is not possible to find the value of this RTH directly. Why it is not possible? Because we don't know what is the internal resistance offered by this dependent voltage source, and that's why we need to apply this technique. That means let us consider a very small value of voltage source, say 1 volt, which we need to connect across this terminal A and B, and let us try to find out what will the value of current supplied by that voltage source. Once we know the value of current, simply take the ratio of V by I to calculate the value of R, and that R is going to be equal to what? RTH. So if you apply this logic, so what we need to do? First we need to connect a very small voltage source over here. Let us consider that this is plus and this is minus, and this value is say 1 volt. So because this is plus and this is minus, it has to supply some value of current in the circuit, and that current is say I. So this current is going to flow in this particular sense, which is nothing but say anti-clockwise sense. This is very important. In the same way, we may have one more current which is flowing in the circuit, which is nothing but this particular mesh. And let us consider that that current is again flows in anti-clockwise direction, and direction is say I1. I need to say I1. So here now we have two current. First is I, which is supplied by this 1 volt voltage source, and then here we have one more current which is going to be flowing this particular circuit in the anti-clockwise direction. Now our objective is to find the value of this I. So how to find this I? Again, we need to apply the logic of KVL and KCL. So first, let us try to apply Kirchhoff's voltage law in this mesh. Which one? Let me show you. In this outer mesh, we are going to apply the Kirchhoff's voltage law. You may read the circuit in clockwise direction, or you may read the circuit anti-clockwise direction. Now I am reading the circuit in the clockwise direction. So when we are moving through this 6 ohm resistor, so I can write here as apply Kirchhoff's voltage law. So when we are moving through this 6 ohm resistor in the clockwise direction, that means we are moving from upper portion to lower portion. So I'm going to experience a voltage rise or a voltage drop. That depends upon what kind of circuit I'm having with me. Now see, this is nothing but say 6 ohm resistor. To one side we have a current like I1, and to another side we have a current like I. Now I'm reading this element in this particular direction. Okay, so I can write here as this is going to be 6. Now suppose I'm writing this equation with respect to this polarity, like I'm assuming that this I is more as compared to I1. So this is going to be plus and this is going to be minus. So in this case, I'm going to experience a voltage drop. So this is going to be minus 6 into. Now what I need to take? It is going to be I minus of I1. I hope this is clear to everyone. I minus of I1. In the same way, when we are moving through this particular resistor of value say 4 ohm, so we are moving in this particular sense. Now the actual current is in this direction, that means I1, and we are experiencing a voltage rise. So here we need to take this as plus, and this is going to be what? 4 into I1. In the same way, when we are moving through this 2Vx, we are experiencing a voltage rise, and the value is set 2 times of Vx. Now this is going to be equals to what? 0. This is very important. I hope this point is clear to everyone. Now let us try to find out or rewrite this equation in terms of Vx. So I can write here as Vx is going to be equals to 4 times of I1, because what is Vx? It is nothing but the voltage which is going to be appear across this 4 ohm resistor. So if you replace this Vx as 4 times of I1 in this particular equation, and let us try to solve this for I and I1, you will get the relationship between I1 and I, like I1 is going to be equals to I by 3. Take pen paper and try to solve this. You will get this equation as an output. That is nothing but I1 is going to be equal to I by 3. That this will be your equation number 1. So how to find out this? Simply you need to put this Vx is equals to 4 into I over here. This 4I plus 4I is going to be 8I, and then club them, solve them, you will get I1 as I by 3. This will be your first equation. Now let us try to find out one more equation in terms of I and I1. And to find out that, we need to apply again Kirchhoff's voltage law, but in this mesh, this one. This mesh, we are going to apply that. So if you apply that KVL, we can write here as, when we are moving through this 1 volt voltage source in the direction of current, we will experience a rise. So it is going to be 1 volt. So I am writing that equation directly. So this is going to be 1 volt. And then when we are moving through this, so this is going to be minus 2 times of I, and then it is going to be minus 6 times of I minus of I1. This is going to be equals to what? 0. This is very important. I hope this point is clear to everyone. This is very, very important. So once you have this equation, now it is very simple to find out the relationship between I and I1. How to find out? See, solve this equation for I and I1. So I can write here as 1 minus, this is going to be like 6 to 8 I1 minus minus plus 6 I1, that is going to be equals to 0. So this is the another equation. Now our objective is to find the value of what I. So I can write here I1 as I by 3. So I can write here as 1 minus 8I plus 6. Now what is I1? It is going to be what? I by 3 is going to be equals to what? 0. So 3 ones are, this is going to be 3 twos are. So I can write here as 1 minus of 8I plus 2I is going to be 0. So 1 minus of 6I is going to be 0, or I can write here as I is going to be equals to what? 1 by 6 ampere. This is very important. I hope this is clear to everyone. The thing is that you need to apply and solve the equations very carefully. You will get a proper answer for this. I hope this is clear to everyone. Once you know the value of this I, we can now find out the value of R, or you can say RTH. So here I'm writing now RTH in this case is going to be equals to V by R. Now we have connected a 1 volt voltage source over here. So this is going to be V, which is nothing but 1 by your I. R is nothing but V by I. So I is nothing but 1 by 6. So here we need to write here 1 by 6. So if you solve, you will get RTH as 6 ohm. This is very, very important. Now finally, in the first portion of this network, when we solve for VTH, we got the value of VTH as 20 volt. And here we got the value of RTH as 6 ohm. Now the Thevenin's equivalent circuit for this case is going to be like this. So here we are having a voltage source plus minus, which is nothing but VTH, and here we got the value of VTH is 20 volt. Then so here we need to connect its equivalent RTH, and we got the value of RTH as 6 ohm, and then here we are having its two load terminal. This is terminal A and this is terminal B. So when you see the circuit from terminal AB, we are going to experience a voltage, or you can say Thevenin's equivalent voltage of 20 volt, followed by Thevenin's equivalent resistance of 6 ohm. So in this way you can solve the numerical on Thevenin's equivalent as well as Norton's equivalent. Suppose if you want to find out its Norton's equivalent, what we need to do? We need to apply source transformation method to find out the value of this I in parallel with its equivalent resistance. So equivalent resistance will remain same. It is going to be 6, and this IN is going to be equals to VTH divided by RTH. So this VTH is nothing but 20, RTH is nothing but 6. So it is going to be 10 by 3. So 10 by 3 ampere will be its Norton's equivalent current source. This is very important. So in this way we can solve the numerical based on the calculations for equivalent voltage source corresponding to Thevenin's and equivalent current source corresponding to Norton's when we are dealing with a kind of dependent source and independent source. The thing is that the calculations for this RTH is very tricky in this case because we don't know what is the internal resistance of this dependent voltage source or dependent current source. And to overcome that problem, what we need to do, we need to assume that we are going to connect a very small value of voltage source across load terminal, and let us consider that the value is say 1 volt, and let us try to find out what will be the value of current supplied by that voltage source in that circuit. And once we have the value of that I, simply take the ratio of V by I to calculate the value of what RTH. So this concept you need to remember when you are dealing with these kind of problems. Now let us try to understand the concept of maximum power transfer theorem. What is maximum power transfer theorem, and how to calculate the value of maximum power when we apply maximum power transfer theorem applied by a source to a load. So according to maximum power transfer theorem, according to maximum power transfer theorem, a maximum power is supplied by a source to a load when the value of load resistance is going to be equal to the Thevenin's equivalent of that particular network. This is very important. So what is maximum power transfer theorem? In a linear bilateral network, suppose if you are interested to find out what will the maximum value of power which is supplied by this particular source to any load, it is nothing but possible only when the value of that load resistance is going to be equal to the Thevenin's equivalent of that network across that particular terminal. This is what the statement for maximum power transfer theorem in case of DC circuit. So let us try to analyze this. What is the meaning of this, and what is the condition for maximum power transfer theorem? Why we have stated this theorem like this only? That means when the value of RL is going to be RTH, then only we can have the flexibility to transfer maximum power in the circuit from source end to the load end. To understand the philosophy behind maximum power transfer theorem, let us consider that we have a Thevenin's equivalent representation of a network which is going to be like this. So here we have a Thevenin's equivalent voltage, which is nothing but VTH, and suppose this indicate the Thevenin's equivalent resistance of the network, which is nothing but RTH. And somewhere over here we have a load terminal, and to this we have connected a variable load of value, say RL, and our objective is to find out the condition for maximum power. And I already told you that maximum power transfer is possible only when the value of this RL, which is nothing but this variable load resistance, is exactly going to be equal to the Thevenin's equivalent resistance of this particular network. So let us try to find out whether that statement is correct or not. Now, because we have a potential difference and the path is closed, so there has to be a current which is flowing through the circuit, and let us consider that the value of current is, say, I. So if you apply Ohm's law, I can write here as this I is going to be equals to VTH divided by RTH plus RL. Let this will be your equation number 1. Now our objective is to find the value of power, or how much amount of maximum power this source is going to be delivered to this particular load. And for that we need to find out the mathematical equation for power 2. So I know that power is nothing but V square by R, or I can write that power as I square into R, or we can write that power as V into I. So I'm using here the equation power is going to be equals to what? I square into RL, or I can write here as power is going to be what is I. So I is nothing but VTH divided by RTH plus RL whole square into RL, or I can write here as power is going to be equals to VTH square whole divided by this RTH square plus A plus B whole square, so A square plus twice AB, so twice RTH into RL plus RL square, and this is multiplied by again RL. Or I can rewrite this equation as power is equals to, if you divide numerator denominator by RL, I can write here as VTH square whole divided by, this is going to be what, RTH square divided by RL, and then plus 2 times of RTH, and then here we are going to have RL. I hope this is clear to everyone. This is very simple. That this will be your equation number 2. Now our objective is to find the maximum value of this power, and this is possible only when the variation of this power with respect to RL going to achieve a zero slope. What is the meaning of this? Now see here, suppose if you want to plot the graph between this power with respect to load resistance, which is nothing but RL. Now you tell me how the graph is going to be like this, or how the variation of power is going to be with respect to RL. Now to find out the variation of this P with respect to RL, just focus on equation number 1, and let this will be your say equation number 3. This one, P is nothing but I square into R. Now see here, the moment we increase the value of load resistance, because P is proportional to I square into RL, so from this, which is nothing but equation number 3, the moment we increase the value of RL, the value of power try to increase. Number 1. Number 2, now let us focus on equation number 1. The moment we increase the value of RL, because current is inversely proportional to this resistance, so when we increase the value of RL, the value of current will try to reduce, and the value of current if try to reduced, here in equation number 3 we have the expression of I, which will try to reduce the value of what, power. So what is the meaning of this? That means initially when we increase the value of load resistance, Corresponding to that, the value of power also increases. But this pattern will continue up to certain point. After that, if we further increase the value of RL, because now the current is dominating in nature, it will try to reduce the value of power. So if you further keep on continuously increasing the value of RL, this will lead to the reduction in the value of what? Power. So if you apply this logic over here, the graph between power versus RL is going to be like this. So initially, when we increase the value of RL, power is also going to be increased up to certain point, and then after that, if you further increase the value of RL, current become dominating in nature, and that will leads to the reduction in the value of power. So it is going to be like this. So at this particular point, we have the maximum value of power. This is nothing but your say P max, and this is going to be happen for certain value of load resistance. And what is this RL? This we need to find out. And I told you that according to maximum power transfer theorem, this value of RL is going to be equals to what? RTH. This is what the statement for maximum power transfer theorem. That means a source is going to supply maximum power to a load only when the value of load resistance is going to be equal to its equivalent Thevenin's resistance. So this is what the variation of power versus RL. It is something like this. Now let us focus on this graph to find out the value of this P max. The slope of this particular graph at this location is going to be what? 0. That means the variation of this P versus RL, or if you take the slope, it is going to be dP by dRL is going to be equals to what? 0. So to find the condition for maximum power, in this case, what we need to do? We need to take dP by dRL is going to be equals to what? 0. Or if you take the derivative of this denominator function with respect to RL and then equate that particular term to 0, because to have P at maximum, this denominator has to be at minimum. And again, to find out the minimum condition, again we need to apply the same logic. That means the slope of this denominator function is going to be 0 at the minimum condition, because it is going to be a flat parallel to your x-axis component. So if you apply that particular logic, so I can write here as d by dRL of the denominator function, which is going to be RTH square divided by RL plus 2 times of RTH plus RL. This is going to be equals to what? 0. So I can rewrite this equation like differentiate this equation with respect to RL. So it is going to be the RTH square. This is going to be your minus RL square, then plus 0, then plus, this is going to be your 1, is going to be your 0. So I can write here as RTH square with negative is going to be equals to minus of RL square. This minus minus get cancelled out here. I can write here as RL is going to be equals to what? RTH. This is very important. So the condition where we have a maximum power which is supposed to be delivered from this particular source to this load is going to be happen when the value of this RL is going to be equals to the Thevenin's equivalent of this network. This is what the proof for maximum power transfer theorem. So the value for this RL is going to be equals to what? RTH. That means when the value of RL is exactly going to be equal to RTH, then in that case the power supplied from source to load is going to be a maximum one. So this is what the proof for maximum power transfer theorem. And suppose if you are interested to find out what is the mathematical expression for P max, so how to find out that? Again, it is very simple. So here I can write like P is going to be equals to your I square into R, and I is VTH divided by RTH plus RL whole square into RL. Now apply the logic over here. That means put the value of RL equals to RTH. So I can write here as P is going to be equals to what? VTH square divided by this RL we need to put as RTH. So RTH plus RTH, this is going to be 2 RTH. If you take square, this is going to be what? 4 your RTH square, 4 RTH square into here. Now we need to replace this RL by RTH. So it is going to be what? RTH. So this RTH and this RTH will get cancelled out, and finally the equation for maximum power is going to be equals to what? VTH square divided by 4 RTH. This is very important. So in this way we can find out the condition for maximum power supplied by source to a load, and that is nothing but when the value of load resistance is going to be equal to its equivalent Thevenin's resistance. And suppose we are interested to find out what is the expression for maximum power which is to be delivered from source to the load, it is going to be equal to that P equals to VTH square divided by 4 into RTH. So this is very important. Once you know the concept of maximum power transfer theorem, now our objective is to solve some numerical on maximum power transfer theorem. How to find out what will the value of maximum power which is delivered from source to a kind of load connected in the circuit. So let's try to solve this numerical. This is going to be first numerical on maximum power transfer theorem, and the circuit for this is something like this. So here we have a voltage source of polarity plus minus 12 volt, and somewhere over here we have a 6 ohm resistor, followed by here we have a 12 ohm resistor, then here we have again 3 ohm resistor, and then here we have again an active element of magnitude 2 ampere, and then here we have a resistor of 2 ohm, and here we have connected a variable load of value RL, and our objective is to find out what is the maximum power which we are going to have across this RL, which is to be supplied by this particular network using maximum power transfer theorem. So how to find out this? Again, we need to apply the same logic to find out the maximum value of power which is supposed to be developed, or which this particular load is going to be received from this entire network. That is possible only when the value of this RL is going to be equals to what? RTH. And to find out the value of that T, it is nothing but what? VTH square divided by 4 times of RTH. So first of all, what we need to do, we have to find out its Thevenin's equivalent network across this load terminal or across this connected load. So we need to find out the value of RTH. Then we need to find out the value of VTH. Once you know the value of VTH, once you know the value of RTH, we can easily find out the value of this power. It is nothing but the maximum value of power supplied by this particular network to this connected load. So this I'm going to give as an assignment to you. Take your time, try to solve this particular numerical. In the next lecture, we are going to continue our lecture from this particular point. That means first we are going to solve this particular network that is based on maximum power transfer theorem, and then we will solve some more numerical based on the same theorem. Let us try to solve this. It's a homework for you. Thank you.